So now we're going to take a look at another category of aqueous reactions that are very, very common. Well, that is very common. And that's the reaction between acids and bases, which we refer to as acid-base reactions, or just generally, we call them acid-base neutralization reactions. And in order to understand this, we first of all need to have a little bit of background in terms of what acids and bases actually are. We've talked a little bit about acids and a little bit about bases before. We've seen that acids can be either strong or they can be weak. A strong acid is one that dissociates completely. We get lots of ions in solution. As a result, it's a strong electrolyte. Sorry. We have lots of ions in solution. And there are several of these that we've seen already: hydrochloric acid, hydrothermic, hydroiodic, nitric, chloric, and some others that we've seen before. By the same token, strong bases are also strong electrolytes because they dissociate completely to give you lots of ions in solution when they do break apart. And a good examples of strong bases are things that contain hydroxide, right? Hydroxides contain the OH minuses. And these would include the hydroxide of the group 1A, so for example, lithium hydroxide, sodium, potassium, rubidium, cesium, as well as the hydroxides of the group 2A metals that are further down, so the heavy metals, or the heavier metals, not heavy metals, the ones that are further down in that group, so things like calcium hydroxide, strontium hydroxide, air hydroxide. These tend to be strong bases. These will dissociate completely in solution to give you lots of these ions, specifically lots of the hydroxide. Okay? That's the key thing for your bases. Weak acids, weak bases, on the other hand, those tend to be weak electrolytes because they don't dissociate completely. So we get small amounts of ions. So hydrofluoric acid, for instance, doesn't dissociate completely. And again, we can tell that from this equation because we have our double-headed equilibrium type arrow. This means that yes, we do get ions. So ions are produced, they're present, but very small amounts of these, which make them, or would make this, each electrolytes. We'll touch briefly now on how we define acids and bases. And we'll come back to this definition or these definitions in a lot more detail if you're lucky enough to stick around for general chemistry 2. We spent several weeks actually on acids and bases in that class. But for right now, let's take a look at two definitions that we'll use to identify acids and bases. The first is known as Arrhenius. And an Arrhenius acid is one that produces in solution the H plus ion. The H plus ion, that's called a hydrogen ion. It is also called the proton because that is essentially is what it is in solution. So HCl, for example, hydrogen chloride gas, dissolved in water, it does produce this H plus. That makes this an acid as a result of that. An Arrhenius base, on the other hand, is one that dissociates in water to produce the hydroxide. And you can normally tell that something is an Arrhenius base because, excuse me, you can actually see the hydroxide in the formula, right? So we do get the hydroxide ion in that solution. We could normally tell something is an Arrhenius acid because in order to produce H plus, guess what you need to have to use this formula. The second definition that we'll see that tends to be a little bit more broad is called the Bronsted-Lowry, or simply the Bronsted definition. But the full name here is Bronsted-Lowry. definition. And this tends to be a little bit more inclusive in that it does address a lot more acids and bases than the Arrhenius definition does. So the Bronsted-Lowry definition just looks at acids and bases strictly in terms of, from the perspective of the H plus, the hydrogen ion, which is a proton. And according to the Bronsted-Lowry definition, a Bronsted-Lowry acid is a proton donor, something that gives up, something that loses, gives up, or donates one or more H pluses. Which then suggests if that H plus is being given up by something, something else has to accept it. And that something else that accepts it is called a base. So Bronsted base is proton acceptor, something takes, accepts one or more proton, one or more H pluses. Okay. So again, the proton is nothing more than a hydrogen ion, an H plus species. So for instance, in this example, we can look down here between ammonia, NH3, and H2O, right? When this reaction happens between these two, the water, the H2O actually loses an H plus, the water here. And where does that H plus go? Well, the H plus actually goes to the NH3. The NH3 accepts the H plus. If the water loses an H plus, it is an acid. If the NH3 gains an H plus or accepts an H plus, it is a base. And when you stick an H plus onto the NH3, you end up with NH4 plus. If you take away an H plus from H2O, you end up with OH minus, right? And you can draw the Lewis structures for these to rationalize this. So there's my NH3. This is my H2O. Okay, so the water here is losing an H plus, and the lone pair from the nitrogen actually is the thing that accepts it. If you take away now, I'm sorry, if you attach that H plus onto the NH3, okay, what you end up with, you still have the NH3. All we've done is we've added now an H plus onto it. And there's my H. Because I added an H plus, this thing's going to have a positive charge, right? NH4 plus. The H2O, right? This then, you take away this this hydrogen here. Yes, hydrogen that was donated. Well, then if you take that away, you end up with an OH with lone pair, and another lone pair. This has a negative charge on it. That's your hydroxide. So that's what's occurring with the Bronsted-Lowry definition. Things are losing protons, those are acids. Other things are gaining protons, those are bases. Now, the H plus ion in solution, so it's very reactive. And it's so reactive in aqueous solution that H plus will combine with water to make H3O plus, and this is known as the hydronium ion. Okay, and this is what is actually present in solution, but not H plus. H plus is way too reactive to exist on its own. So it actually grabs a hold of any water around, and in aqueous solution have lots of water molecules. So it actually exists in the form of H3O plus. So the point here in explaining this is that you will see H plus, the proton. We will see the word proton. We will also see H3O plus, which is the hydronium. All of these refer to the same thing. They mean the same thing, all of them. One is just used in preference to others, just in instances of simplicity, or we need to write things fairly quickly. They all mean the exact same thing. So don't get confused. If you see any of those three terms, they all refer to the same chemical species. So when it comes to our acids, we said acids are things that donate protons. Certain acids are able to donate more protons than others. An acid that only donates one proton is known as a monoprotic acid. We've seen the term mono, or the prefix mono before, mono meaning one, and protic meaning H plus. The monoprotic acid has one proton to donate. HCl is a good example of this because you can actually just see that one proton in its formula. So we say it has one equivalent of hydrogen ion to donate. Polyprotic acids, on the other hand, can donate more than one proton. So poly here meaning many, and then protic again meaning protons, H pluses. And they have more than one acidic hydrogen. And acidic just means H's that can be lost. Because there are other H's in formulas that are held tightly, and other H's that are lost. The ones that are given up or donated or lost, those are called acidic hydrogen. So some examples. Sulfuric acid, H2SO4, has two H's. So this is known as a diprotic acid. It can lose those two hydrogen atoms, but it does so in a stepwise fashion. So it loses both H's, H pluses in two steps. So the first step, this H2SO4 here loses that first H plus. So we take away an H plus from this. We end up with an HSO4 with a negative charge, and there's our H plus that's lost. And then the second H plus is lost from the HSO4. We take away this H plus here. Okay, that's gone. Now we end up with SO4 with a 2 minus charge, and there's that H plus that is given. Okay, the first H plus is lost very easily, which is represented by this regular looking arrow. The second H plus is not lost as easily, so it's actually more of an equilibrium situation. So we see the double-headed arrow instead. Just as your acids can give up, they can be mono or polyprotic. Your bases can also give up either individual, one or more hydroxides per formula unit. Bases that produce just 1 mole of hydroxides, these are known as monobasic bases. Sodium hydroxide is a good example. And again, you can see just the one OH in the formula. There's the one equivalent of hydroxide that's given up when this dissociates in solution. We can have examples where more than one hydroxide is donated or lost. Barium hydroxide, for instance, look at the formula. There are actually 2 hydroxides in it, so it's called a dibasic base. So when this dissociates, we get the barium 2 plus and get 2 equivalents of hydroxide being donated.